Hi, in this video, we want to take a look at clustering with scipy within Python. Specifically, we're going to look at the VQ groups of functions within the cluster portion of the scipy package. All right, so we have two major types of clustering in general in machine learning. One is partition clustering, the other one is hierarchical clustering. The other major type is model-based clustering. Here, we're going to talk about the partition clustering. Here, what we want to do, we want to take all our rows of data, which are numeric data, 100%, and we want to group them into subgroups that have similar data features. Okay, so why would we like to do this? Well, one, I could be doing this for segmentation. So what I want to do, let's say I have 1 million clients that I need to work with, and I have a team of 1,000 auditors, 1,000 employees, something like that. And I need to break up all of my clients into subgroups and assign the subgroups to each employee. So what I want to have happen is I want each one of those employees to be like a specialist and really understanding who their clients are. So I want to group clients together that are similar to each other. That way, whoever has to work with them will have more insight into each individual client from experiences from the previous client interactions. So customer segmentation is one reason. Another reason could be that we believe that there are subpopulations in our data, but those are not included inside our data set. And we're going, hey, I think there's subpopulations. I want to find those subpopulations and figure them out. Now, if it's not labeled in my data, I have to use some algorithm, some data technique to do this. And so we're going to use partition clustering. Another reason to do this is for outlier detection. And I'll show an example of this in this video. So for outlier detection, the idea is if I do clustering and I end up getting an observation that's by itself, or maybe just a few in that cluster, then I believe that those observations in that small subgroup are outliers or anomalies. Something weird's going on with those guys. All right, and see, another reason why we would want to do this is we could potentially use clustering to create a categorical predictor variable inside of a supervised learning process. So major reasons: customer segmentation, subpopulation estimation, outlier detection, and then predictor variable generation. Okay, so feature engineering. All right, okay, so what I'm going to do, I'm going to run through an example. I took this data from the City of Orlando's website on their open data portion of the website. This is data for officer-involved shootings, and this is from the entire data set that they had posted. Okay, so I have it saved as a CSV on my machine, and here is file name. Here I'm going to extract only the numeric columns because we are working with numeric values when we're doing k-means clustering. So for this video, we're only going to do k-means clustering. We'll talk about other versions later. And so here's my actual data. Now, some things should jump out at you immediately when I say this is numeric data and you look at this. You'll notice, well, we have a missing value here. We have commas here. We have character string here. Okay, so there's some problems with this data. So we need to clean this up. So what we're going to need to do is we're going to need to go through, and I'm going to go ahead and replace, anytime I have multiple entries in one cell, I'm going to replace it with the median of that cell. Then on top of that, I'm going to go through every time I have a missing value or a character string, I'm going to replace that with the median of the column. Now, when we do k-means clustering, if I have one missing value, that observation cannot be part of the modeling. it just won't work out. We have to do something about the missing values. So you have to make a decision, choose what you're going to do. Here I'm doing median imputation. All right, so here in this part, I'm going through and I'm splitting the cells that have a comma by the comma, and then I'm taking the median of those values. The rest of this is just for me to be able to compute that. Really, the part to focus in on is the split on the commas, and then, well, then I'm converting to a float, a numeric value, then I'm taking the median. And then I'm replacing the entry with that. All right, so that's good. Now, on this next step, what I'm going to do, I'm going to simultaneously convert all the character strings that are inside my data set into missing values by converting all the columns to numeric and coercing them into numeric values. Or when I do this, every time there's something that cannot be converted to a numeric value, it's going to get converted to a missing value. You'll notice up here when I got all the data, I put it in as a string because at this step, I want everything to be consistent as I work through. It probably would have been better to do it in the read CSV portion to say everything was a string, but I did it here instead. For this video, it won't change the output. All right, so here everything has been converted to a numeric value from a string, and anytime I have something that cannot be represented as a number, it gets converted to a missing value because I put coerce in there. Now I'm going to go through, I'm going to go column by column. I'm going to compute the median value of the column, and then I'm going to fill in all missing values with the median. Now, when I do this, I am filling in my data with really a fake number. So when you impute, make sure you do this with considering the problems that could come up. Anytime you impute data, you are creating fake data. It is reasonable for stakeholders to object to this. And on some projects, this can be a very bad idea. Also, just from a data science point of view, also, if your stakeholders are not comfortable with this machine learning idea, or they're very very aware or cautious of problems that can arise from fabricating data, you don't want to do this. And so another option would be to omit those values. If you look at the data set, there's only 72 rows. That's not very many in terms of data science. Therefore, I'm going to go ahead and just keep all my rows of data instead of kicking them out. Another option would be to omit rows that have one or more missing values. And so here we have our cleaned up data. You'll notice that I have officer age of 33.5 here. That, if you think about it, that doesn't really make sense. I mean, when was the last time you heard a 33-year-old adult going, I'm 33 and a half? No, that's because it's the median value. They're not like, in preschool age talking about, a half a year age. All right, so what we want to do, we want to do k-means clustering. How k-means clustering works is that what we're going to do, we're going to just kind of establish some centers in the higher dimensional space of the data. Then what we're going to do, we're going to see for each point, we're going to see which centers are closest to each individual point. All right, so in the examples I'm going to give, I'm going to pick two centers. Then I'm going to run through all 72 observations. I'm going to see which of these two centers is closer. All right, if the first one's closer, they're all going to be put into the first group. If the second one's closer, all those are going to be put into the second group. Now, what's going to happen after that, after I have that initial grouping, we're going to take all the data that's in the first group, take averages, that's the new first center. We're going to take all of the points that are in the second group, take the new averages, that's the new second center. Repeat this over and over and over until it looks like we've got everything how we want, that everything's good. All right, so now let's look at the whiten function in scipy clustering. All right, so something about the k-means algorithm that may not be obvious from what I described is that columns that have more variance, more standard deviation are going to have more influence on the model. Think about the situation where we had running times in seconds and we had the 40-yard dash, 100-meter sprint, we had 200-meter, 400, 800, 1500, 3000, and the marathon, all in seconds. Now think about the size of the numbers. If we're talking about 40-yard dash, that's going to be just a few seconds. Talk about marathon, those are going to be some big numbers. All right, what we could expect to see in that situation is that when I do my clustering, because the variance is so big in the marathon aspect, just because not because there's that much spread, but just because the magnitude of the numbers are so big, the marathon numbers are going to be so large that the variance is going to be bigger. Therefore, the algorithm to get better groups is really going to hyper focus on that marathon column. And it's going to virtually ignore the 40-yard dash and the 100-meter sprint. All right, so then if that's what I want, that's good. Everything, I just leave it as is. But if I want all columns to have equal representation in the model, what I need to do, I need to make sure that all of the columns have the same variance standard deviation. Okay, so the whiten function goes through and makes sure that every single column has the same standard deviation. All right. And to do this, all I gotta do is just take the whiten function from scipy, and you'll notice I have a data frame coming out. And so here is the whiten function. I'm putting in the numeric values. Check finite. All right, so what this does, and now the check finite is used in all functions in this video. Check finite double checks to make sure that everything I'm working with is a relatively well-behaved number. All right, now if I have a large data set, this can take a long time and this can slow down the system. If I set check finite to false, that can speed things up. Now there's a downside to that. If I have problems in my data that I have not already dealt with, which I have here, then I won't know that I'm getting a problem until like I launch the model and I start having problems with my stakeholders because I built a crap model. So set check finite to false to improve computation speed, but make sure your data is well prepared before you do this. And so here is the standard deviation rescaled version of the data. Now you'll notice that this is different from center and scaling. Centering subtracts off the sample mean, then divides by standard deviation. Here, we're just dividing by standard deviation or something close to it. And so we can, if you look here, the range of values is pretty constant in terms of difference between maximum and minimum. Now, it's not exactly constant, but eyeballing it, you can see that things are relatively consistent. All right, now to show you that we have put everything on the same standard deviation scale, I'm going to go through and just print out what the standard deviation is. And we can see that we get the same standard deviation every single time, almost up to round off error, it's all the same. I was kind of surprised when I saw this output. I thought it would be exactly 1. It's not. The main thing is that they need to all be equal in terms of the standard deviation. If they're all equal in standard deviation, all columns will have equal influence in the model. All right, and here is just some summary statistics of each column. Now let's actually run k-means clustering. So there's 2 versions of k-means clustering, k-means and k-means 2. We're going to look at k-means first. All right, so what we're going to do, we're going to give it some data that we want to cluster on. We're going to specify the initial centers in some way, some shape, some form. Now, the number of iterations of that group together, recalculate center, group together, recalculate center, over and over and over. Here we're saying do that most 20 times. And the threshold is a threshold for when to stop. If the center values of the clusters don't change very much, and here when I say very much, that's the amount. If they change less than that, then it'll stop early. Now the k-means algorithm is very fast and it's a very good choice for large data. Once again, we have check finite, same as before. We can improve computation time, but know that you're running a risk. And we can set the seed to make it reproducible. All right, so let's look at this. All right, so the thing I want you to pay attention to between these two blocks of code, they're the same function. I've got the same parameter values, except for here, where I'm specifying what the centers are. I'm manually saying I want these centers. Here, I'm specifying take 2 centers. All right, so here I'm saying here are the initial centers I want you to go with. So I want 03031 to be one of the centers. I want 78797 to be the other center. What's going to happen with all 72 values of the data? For each data point, it's going to check to see which of the 2 centers is closer, and we're going to group all the ones that are closer to one into one group, all the ones that are closer to the other in another group. Now I have an initial grouping, recalculate the center. So take the average of everything in this group, take the average of everything in this group, then recalculate and rerun this whole center business all over again. And do this at most 20 times. And so here are the centers that we get after running that. So this is the average of the whitened values that are in the first group. This is the average of the values of the data that are in the second group. Now here, this tells us what is the average Euclidean distance between observation and its center. All right, so we would like for this to be a smaller number. Now here, what I'm doing, the difference between this and this is that I'm up here, I'm saying these are what the centers are. Here I'm saying pick 2 observations and run with it. Pick 2 observations. Now you'll notice I don't have control of what those values are. I'm just saying pick 2. It's going to do that using a random number generation, and then it's going to run through the process. Now, I strongly recommend that you actually specify your initial centers. Why do I recommend that? Because this makes it 100% reproducible. Okay, something that can happen is that if I'm setting up this value, I say to randomly pick 2, it may or may not pick the same next go around. Even if I set the seed, if things change about the version of Python I'm using, or I get a new machine, maybe a coworker uses my code and they've tinkered with the settings on a random number generation. Something like that can make it so that one run to the other, even though I try my best, will not produce the same results. This is one of the few times I can have a 100% reproducible process when there's like a random seed aspect going on. And so I strongly recommend that you manually set up what your seeds are. But for most cases, it won't really matter. But just to make sure you get the same thing every time, I recommend doing it this way. Now, I could not get the seed parameter to run on my machine. I don't know what I'm doing wrong, but for none of the functions, none of the examples I give you in this video, seed ran, so I just omitted it. I was going to set it to make things reproducible down the road. All right, so with regular old k-means, we get the centers, which is called a code book, and we get the average Euclidean distance between points and their center. Now, let's look at another version of k-means. All right, so this is a little bit different. operates very similarly. The main difference is in the amount of control that I have over what's going on. Things are, for the most part, the same, but in my initialization, I have more control over what's going on. I can say that I want the system to go estimate a multivariate Gaussian distribution off of the data and then randomly generate the centers. I can tell it to select points to generate the centers initially, which is similar to the first algorithm. And now here, this is a modified version with the plus. And then we can also pass a matrix of the centroids, which is what I recommend you do. Now here, we also have options of controlling what happens when there's missing values. All right, so either we can say, throw a warning, but don't stop if there's a missing value, or we can say, hey, shut the whole thing down if there's a missing value. All right, so here, I'm going to just run through. I'm going to do exactly what I did before, but now I'm using k-means 2. I'm setting up the initial centroids. Now, a difference here in k-means 2 is that the maximum number of iterations is 10 instead of 20. Not a big difference. This algorithm converges fast. It's usually not an issue. It might be a bigger deal if you have a larger data set, or if you're choosing, like, imagine a situation where we have too few centers for what our data is having. If I have subpopulations and spread out in higher dimensional data space, then I will need, if I had more initial centroids, I would be better off on trying to, get it to converge. If it takes a long time to converge, that's a sign you have a bad model. All right, and so here we can see we got centers that are very similar to what we saw before, a little bit different. Now, something that's different with k-means 2 is it spits out what group each data point is in. So remember, in Python likes to start at 0. And so 0 is like the first cluster and 1 is the second. So now, check this out. There is only one value, 1 point is in cluster labeled 1. Okay, I see that. That tells me that that point is probably an outlier. It's by itself. It's in higher dimensional space. It's so far off from everybody else that in the clustering algorithm is by itself. So here I am concerned that this data point is an outlier. If I was running an algorithm or a study, I would definitely want to look deeper onto this value before going further. I more than likely would want to double check the values and more than likely be prone to omitting it if that makes sense. Or I might have to report, run my report and say, all right, I include the data point, but there is this point that is atypical from the rest. Now we can also do the random aspect. So here we are telling Python to go estimate multivariate normal distribution, then use multivariate normal to give me my initial centroids. Here we're saying randomly select 2 points from the data sets. Here we're doing the plus version, a slight variation on the algorithm. And so we have all these options. I personally like the points after specifying what I actually want for the initial centers. But whatever works for your project, worry about your stakeholders and your supervisor to make them happy. That's your most important step in data science. Because if they're not happy, your model won't be used. There's no point in your work. All right, so now, after I have my clustering, I need to be able to take new data and assign them to the groups. All right, so I've already done a k-means clustering. Now, what's going to happen is a new data set is going to come, and I need to decide which group does each observation go into. All right, Well, to do that, I'm going to use the VQ function. What this is going to do, it's going to go through and it's going to take the data. It's going to find which of the resulting centroids are closest to each of the data points, and then assign the new data to the appropriate groups. Now, something that is important about this is that you need to make sure that your new data is on the same center and scale aspect as the data that the model was fitted on. So here, if I had new data coming in, I would want to rescale by the same value that the original data was rescaled by. All right, so what I want to do, I want to go in and I want to take the VQ function and I want to take a code book, which is the centroids of my k-means model, and I'm going to say, hey, here are the centroids from my k-means model, assign each one to that. All right, so how do I do this? In my k-means output, there's two outputs from k-means 2. There is the centroids and there's the labels. All right, so the labels connect with each data point in the training data. So every data point that I use to build the k-means model gets a label that's put here. So the first one, second one, third one in my data correspond to the first, second, and third entries of this vector. This is going to be the centroids of that. So I can show you, we'll scroll up. These values are my code book, this 2-row array of numbers. And so that gets put here in the code book. And now here, I'm just going to go ahead and just use my whitened data. Remember, the data I put in on this step must be on the same center and scale range aspects parameters as the data I use to build my model. If that's not the case, it's going to be a garbage in, garbage out moment. Now, to see which value is the outlier, I'm going to say the code numeric equals 1. So here is the output. So this is all of the labels, and this indicates the distance from each point to its center. And so now when I do this, when I take the original data and I find the cluster with only one observation, boom, look at this. This is interesting. I mean, what? Number of officers involved, 11. There were 11 officers involved in this incident. And so we have all of these ages. They were all men, ethnicity, looks like none and 1 or 2 Hispanic. Most are white, 2 black. I mean, it's a bunch of, a bunch of officers were involved in this. Now here, this is the distance from each point in the whitened version of the data to its centroid. And so this gives us an indication of how well each point fits within its cluster. And so here, when I see a 7, that could mean that that point might actually belong to a different group. The larger the value, the more I'm worried that it might be in the wrong group. You'll notice that here, that's a 0 because that point was off by itself. And so it's by itself, it is its own centroid, therefore it's a distance of 0. All right, so to recap, when I'm doing k-means clustering, I must have everything, all my data on the same scale. And when I score data, that data must be on the scale of the training data also. We have 4 reasons for going through and doing k-means clustering. First and foremost, segmentation, subpopulation detection. We have outlier detection, which is what we did here. And we have feature engineering of creating a categorical vector. Well, that's all I've got for you. Take care and goodbye.